Yeah, we can hear you.
Okay, my name is Genevieve. I'll be presenting on behalf of the Breast Cancer Project Group. Okay, and we have the table of contents, the abstract, introduction, aims and objective, methodology, results, feature selection and its significance, the challenges, conclusion, and recommendation. So the breast cancer actually is the cancer of the breast, and it forms in the cells of the breast, and it mostly affects the women. One of the symptoms of a breast cancer is actually a lump in the breast, and various tests are always carried out in this lump to prove if it's actually malignant, that's a positive or cancerous cell, or benign, that's a negative or a non-cancerous cell. So this project actually tends towards reducing the length of time at which it takes to predict a malignant or a benign lump by training a model using the data set which has the features got from the various tests recorded from tested patients. So the steps we actually used in this project was to get the data sets, analyze the data, visualize it, pre-process the data, train the model, test the model, and evaluate the model. And conclusively, based on the comparison of the various machine learning classification algorithms that we used, that's the logistic regression, k-nearest neighbors, support vector classifiers, the linear and the radial basis function, and the rest, we're able to observe that the random forest classifier was observed to perform best on the text data with 98% accuracy. Introduction of the topic, the breast cancer, predicting benign, that's a non-cancerous cell, or malignant, a cancerous cell in lump found in a patient's breast. So as we all know, the breast cancer actually is the most common invasive cancer in women, and it is actually the second leading cause of cancer death in women after lung cancer. And there's actually a possibility of detecting this cancer at an early stage based on the features collected from patients, and these features form the data sets that were provided with to build a model that will predict if it's actually malignant or benign. The aims and objective of this project which we observed was a binary classification, is to observe which of the features provided helps in predicting malignant or benign cells in a lump. And we actually were to analyze the data, build a model that would detect the cancerous cell with good accuracy. So the methods we used for this project was to explore our data sets. Then we use different type of visualization, like the swarm plot. The swarm plot actually showed us a distribution of our target variable in each of the features. That each of the features we provided, I'm sorry, I don't have an image after this. Each of the features provided, we did a swarm plot to show the distribution of the benign and the malignant cell in each of the features, yeah. So then we did the correlation matrix, frequency distribution, and order. Then after that, we did the label encoder. We changed the cell type of the diagnosis column, which by domain knowledge and also by intuition, we knew that was our target variable, because our target variable was to predict a benign or malignant cancer, and that diagnosis had benign or malignant, but it was in object, so we had to use label encoder to change to change it from an object to a binary number, like 0 for benign and 1 for malignant. Then we did the train test split. The train test split was to split our data sets to a trained data set and a test data set. Then we scaled the features. We did the standard scaler to scale the features so that all the features can have the same mean of 0 and standard deviation of 1. More like to make them balanced so that we don't have to avoid bias in our algorithm. Then we use the classification algorithms. That's we use different machine learning classification algorithms like the random forest, the logistic regression. Then we did our model evaluation. So now from the first picture on top showed the different classifiers and their accuracies. This was for the trained data set. So we had in this trained data set, the decision tree actually had the highest accuracy. But when we did it with the test data, I don't know if it's clear enough. Our Random forest has 98% accuracy compared to others. So it actually had the best accuracy. So from the results we got, we're able to observe that the random forest performed best with 98% accuracy. The image on the top left was actually a plot of all the classifiers, and we can see the random forest, which has a purple color, ranking higher than the rest in their accuracy levels. This is using the confusion, the evaluation metrics. This is the precision part. This is the random forest classifier. This is the recall part. This is the random forest classifier. So when we did this evaluation metrics, we were able to see that the random forest classifier showed to have a higher accuracy in it. Then we did a confusion metrics of this random forest classifier on our test data. So this image is actually on the random forest classifier. So our data set actually had a 90 benign patients, but our classifier was able to give us our benign is actually negative, and our malignant is actually positive. The data set we had 90 benign patients, but our classifier was able to give us 89 negative and 52 instead of 43. So the remaining one became our false positive and our false negative. So we did a feature selection. We decided to reduce our features to see how it was going to affect our initial classification accuracies. And we reduced it from about 32 to 16 features. So this image on the left is actually the correlation matrix of the reduced features. It was actually 32. Then this picture on the right is a picture of the significance of, or rather the accuracy of these new features with the old one. This new accuracy with the old one. So from the comparison made, this SVC radial-based first had before 0.972, that's 97.2%, and has these selected features, that's the reduced features, as the same thing. And the random forest had 98, but in these selected features has 95. The logistic creation had 95, and in this selected features 96. So we decided to just show a little of the difference or the little changes that was made in the accuracy. So some of the challenges my group members and I faced during this thing was trying to understand which classifier to use or not to use, the use and understanding of the evaluation metrics, which to use, and reading the outputs. Some people had problems with cleaning the data, that's actually using the label encoder to change to a binary number. Some people had problem with the feature selection, knowing the one that was not important to use or to drop. Then some people had problem translating results and visualization. I think we had a pair plot, but visualizing it was too strong that we just had to comment that out for this slide. So our conclusion actually in this project, we successfully utilized most machine learning classification algorithms to understand how these different classifiers work and their different accuracies. And based on the feature selection we did, we're able to see that, which was from the image I showed of the selected features, we're able to see that there was no so much of a worsen or improved significant change to the algorithm accuracies, hence only suitable for feature analysis or model simplification. So what we'll be recommending is that this random forest, we have 3 recommendations because it was a group work. So I decided to put all. We had this recommendation from that the random forest classifier be deployed for use in hospitals for the prediction of malignant or benign lumps in patients. And also we can have a further research in using an ensemble of these classifiers, maybe two of the classifiers to be used together to help in predicting benign or malignant cancer. Then also a model can be embedded in an app where cytology results, that's the results from a lump test, can be imputed to make prediction based on a scale like 1 to 10. We can have, okay, the model predicting if it falls between 1 to 4, it's benign. If it falls in 5, it is pre-malignant. If it falls in 6 to 10, it is malignant. Thank you.
Thank you, Genevieve. So I got carried away. I was supposed to take pictures and then I got carried away. So please just help me go back a bit to your plots. Pardon me. Like the presentation was so nice and then I got carried away. Okay, let's stop here first. Sorry. Can you go to the first one? The first page. So while she's doing that, we can start preparing. Maybe Teju will go first. Okay, go to the first page, not the introduction. We're almost there.
This is the first page.
Okay, nice. Okay, give me one. Okay, so Teju, you can start. You can start. Is Teju on the call?
Yes, I am. Nice presentation. Well done to you and your team. I have one thing which I said from the last speaker is that there's a lot of text. Yeah, there's a lot of text, and we could benefit a lot more with plots. And I'm sure that you and your group will take that as a feedback. But besides that, so I was going to ask you, let's say you wanted to, what would be your recommendation to, like, how, if a doctor needs to use something like this, how would it be useful to them? How do you think it would help in terms of, like, in the real world scenario?
Okay. The part of deploying the model into maybe an app can have after a test of each lump, because they use a fine needle aspirate biopsy to extract a sample of a lump in a breast and do a histology on it. So after that test is done, I don't know, it has to be done in a way that the extracted sample of a lump can be passed into the model to then predict if it is benign or malignant, because it's still that extracted sample that they have to go over to know if it's actually, they have to do several tests and wait some days before a result comes out. So if it's, I don't know, maybe a picture of the image, the lump sample can be a picture, have maybe computer vision of the lump sample image, pass through the model and have it predict if it's benign or malignant.
Yeah, that would be a great suggestion. Instead of having to go through that lengthy process of extracting the features by getting all those columns and then passing it through the model for prediction. It would be great if we can just like take a picture, just like you said, or a scan of the breast and have a computer vision model help us figure out what exactly in this breast makes it a breast. What part should I focus on? And also, so maybe it's something that could be a future direction for your project if you're really, really motivated / interested in breast cancer, and there's a lot of research ongoing, so definitely there would be a lot of literature for you to check out. Recently I also attended a talk by Yetunde Sani. Some of you might know her. She's a master's student at Sapienza University doing AI robotics, and our project is about it's about early detection of breast cancer. So the way she's going about it, because like she said, she's a robotics student, so they are it's more like hardware plus software. So they are doing inverse reinforcement learning, whereby they get an expert to they have like a bra, so to say, with a lot of sensors, a dummy breast. So the expert is going to perform a couple of examination on the breast, and they would on the dummy breast, of course, and they will try to record each of it as a sample. Like you can almost imagine a number of like data sets that they're going to be analyzing. So after collecting a lot of those data, they want to be able to train a reinforcement learning model in such a way that they can be able to the model can do the examination just like the experts would have done it. But then there is a concern, right, which they already like know from their projects, is that they're like different kind of breasts and they're in different shape form. So they would need to have a lot of those diverse kind of breasts to be able to collect different data and know X and Y Z work. But I thought it was an incredibly interesting project, and I was so happy to listen to her talk about it. So I just wanted to mention it as a, just for you to understand that this is like a good project, and it's something that you should definitely not stop working on from now on. You should continue to think about it and continue to read up and try stuff and see um, how you can better use the models you're building to better help save lives. To be honest, these things can save lives. And last thing I wanted to mention is that, and because now everyone understands the importance of machine learning, especially in Africa, and we realize that we don't have enough innovation, and the way we can take ourselves out of poverty really is by innovating. So we need to be, and then there are all these innovation funds that is out there, but but does not have people, there are funds, money out there, but we don't have projects, or we are not thinking big enough, or we have too many issues that we think is limiting us, but we need to start from somewhere. So imagine if you think long term about this project and you're like, oh, okay, so this might be expensive, but that's not the problem. There is an innovation fund. You can submit a proposal. You can have a team and all those stuff. So for people that are interested in like taking their projects forward, if you have good enough projects, well-defined problem statement, you don't have to figure out all the parts, but you need to be motivated, know how it can help save lives, or help make things better, whatever dimension. Then we can think about packaging this and submitting to the Indaba Innovation Fund that having fun. So thank you for your time and for allowing me to talk for this long.
Thank you. Okay.
Thank you. Okay. So Ikechukwu, I think you should go next.
Okay, can you hear me?
Yes, I can.
Okay, Genevieve. I must say that I like the fact that I could hear in your voice someone who really cared about the topic, because oftentimes, beyond just the numbers crunching and models, one of the ways of really getting good at machine learning and the general world of AI is actually finding something that interests you, and putting your mind towards finding ways of solving such a problem. I could hear it in your voice that this is something you actually, you put a lot of thought into it, even if, I don't know if before this, whether it influenced choosing this topic, or when the topic was chosen, you realized it as something important and put your mind into it with your team. But what I would say is the presentation was, I like the flow of the presentation, although like Teju said, would have loved more charts to make it, drive it home. But in all, I think it's a good one. But towards the end, where you did feature selection and you reduced the amount of features, what I would have loved to know is, okay, from your recommendation, it's looking like you're still sticking with the one with all the features, as opposed to the model that the model performance after you selected, you reduce the amount of features. I know that there's also the part about beyond just accuracy of the model. You're also considering how to use it. Is it going to be too heavy? So I think it's something you should also consider with respect to in the sense of using it in the field. Maybe the one with the reduced features could be an option where you can now do maybe something like an exemplar, combine several of those classifiers you did to even create a more powerful model using those few features. But in all, good work.
Thank you. Hello.
Okay, so George, do you want to go next?
So basically, I think the presentation was a good one. Just like what Ike said, the flow was awesome. Like it was more or less like a storytelling, which I think that's what you do in data science. Like you tell stories with your data. And the most important thing is you give useful insights. So what I can say about it is that your visualization was on point. I like the fact you did model ensembling, which is actually great. And I like the application part, like you actually looked beyond building model and you actually thought about deploying it, which is a great one because most times people don't think about model deployment. They just build model and everything dies in the Jupyter notebook. But this is actually a good one. You're thinking about deploying the model on a mobile app. And yeah, it is actually a good one. So I have a question. So my question is this. Did you investigate the false positive? Like, why is that? Why is that value? Like, why is that actual value? I think you got like one on both sides. Why is that? Why is that value wrong? Like, did you investigate that? Like, did you actually look at that data point to see what was even major? Maybe that value, maybe that data point is actually is just incorrect, it's just wrong. Maybe it's just as a result of error from the person that imputed the data, or maybe something else, or maybe it's just noise. Like, did you do that? Hello?
Hello. Yes, I don't know. I don't know if I can ask if any of my group member can also join in answering.
Yeah, of course. It's a group of.
Okay.
Hello?
Yeah, we
Hello?
can hear you, Damilola. We can.
Okay, yes. Thank you very much. As regards that particular data point, I do not think it is noise or something, because it's kept reoccurring. I think SVC and some other models picked it together with some other data point as well as being false positive and false negative. So I couldn't figure particularly which feature was like dancing off point because of the large number of features, but I just sort of overlooked it at the end because it felt small and is like forgivable.
Or is it an outlier or something?
No. I truly doubt that. I'm not sure. I'm not sure precisely. Anyways, I doubt if it was an outlier. I plan on checking more, sure, but the fact that other algorithms also classified some 3, some 4, some 6, and they were not necessarily outliers in all features. Like the fact that the number of features are much makes it hard to know. Some feature might be some point might be an outlier on a particular feature, and it's well in line on another feature as well.
All right. And someone was mentioning the future of this project. So I think you should start looking into, if you're really interested um, in solving breast cancer, if you're really interested in breast cancer problems, I think the next phase of breast cancer is medical imagery. So you're not going to be dealing with all these features because, okay, let me give you an instance. So another source of error might be as a result of the instrument you used for gathering your data. Maybe one of those instruments used for taking these measurements might also be a source of error. So, but with medical imagery, you won't be looking into that space because, you can also have errors from your image, for your medical imagery, but it's kind of, you take the human out, and you just build like different level of abstraction, probably using convolutional neural network to solve it. This is just a computer vision problem. So in that situation, all you just have to do is just probably train a CNN that will extract these features for you instead of actually getting humans to extract these features. So I think it's a good one. You should look into that space. And personally, like what I will grade you on is the application. Like I like when people talk about application. I will also grade you on the storytelling is awesome. And every other thing is just ML practice. Awesome. Yeah.
Thank you.
Thank you.
Thank you, George. The man.
Okay, so nice one, Genevieve and team. Okay, so I'm a bit interested in the feature selection. I mean, you didn't talk about how you did your feature selection. You just said you dropped some features and you checked, and the difference wasn't much, and then you used all of it again. So I don't know how you handle the feature selection. And when you showed the correlation plot, I kind of saw some highly correlated variables. And I don't know how you handle that if you also still fit all of them into your model. Yeah, but also, lastly, what I want to talk about is something that I think it's also kind of doing, is the evaluation. Everybody's jumping towards accuracy. And in this scenario, especially when it comes to health matters, accuracy is might not be the best bet, because your teammate mentioned that, I mean, since it was one, it could have been overlooked. But then that's looking like one death or somebody living with cancer and the person doesn't know he's living with cancer. So accuracy might not really be like best bet in this kind of, classification problem, especially with regards to health, because that one person now that your model said, the person, like the cell is not cancerous. Meanwhile, the person is actually living with a cancerous cell. It's like a very deadly situation. So just think of that in real life scenario, 1 out of every this. So that's like life lost. I'm not saying like you could always try to push to get like 100%, even though that's like the goal. But the thing is, accuracy might not really be like the best scenario. So, I mean, you might want to use like recall in most of these cases to try to check that. I don't know. So I'm also just going to drop a link on this group on the chat that actually talks about like a lot of accuracy metrics or evaluation metrics and what you should also pay attention to based on different problems, because that will also help you in knowing what metric to choose for what kind of problem, depending on what you're working with. Yeah.
Okay. Thank you so much, Udeme. Thank you so much. Okay. It's almost 12 already. And we have 3 more groups. So which group is going next? I would say customer segmentation. It's customer segmentation.
I have a.
Okay, you have one?
Kenichi,
Yeah?
is it possible that we continue the presentation next week? There are 3 more. We don't want to rush this, do we?
Yeah, I think next week will be cool. Yeah.
Yeah, I think we